Okay. So we're going to look at why reactions happen or don't happen. And I've already given an idea of how we can determine if something happens, because we have that delta H value, and we know that exothermic reactions, as far as the universe is concerned, are kind of downhill. Things like to lose energy. If I let go of a ball in midair, it's likely to fall. As it does so, it'll lose potential energy, turn it into kinetic energy and heat energy, and the energy will be dispersed. Whereas endothermic reactions are uphill. They're much less likely to happen. Most reactions you know about are exothermic. And the ones that happen very easily, like burning, once you get something burning, it just keeps going, are very exothermic. But there's something else going on as well, and that's that there is a tendency of things to tend towards disorder. If I pour a box of marbles onto the floor, they will spin off in all sorts of directions, and it's very unlikely that those marbles all over the floor will end up reorganizing themselves into a tight little group in the way they start off. So this measure of disorder is called entropy. At first, you might think, how do you measure disorder? Either your room's a mess or it's not, but you can't quantify it. It's 0.685 of a mess. But this comes from information theory and statistics, and characters like Maxwell and Boltzmann had some input into this. If I have a box with some particles in it, let's keep it really simple. Let's say there's 4 particles in it, 4 gas particles. Then those 4 gas particles could be in a neat little arrangement down one end. There's kind of only 1 or 2 ways of doing that. Whereas if they're randomly distributed around the box, there's many more ways of organizing those particles randomly than there are organizing them in a tight little group. So the number of ways of organizing things, this might have some resonances to people doing maths, and they do permutations and combinations, and statistics, plays into entropy. That's how we put a figure on it. Obviously, we don't have to do that in the chemistry. You just have to know that it's there. What you should know is that in terms of the amount of entropy, well, solids being fairly organized don't have much entropy. Liquids, where the particles are moving around randomly but still close together, have more entropy. And then gases, way up the top there, have lots of entropy because the particles are far apart and moving rapidly and randomly. If you think about an aqueous solution has a few, whatever it is, sodium chloride particles surrounded by water. Those sodium chloride particles, or sodium particles and chloride particles, are very far apart and don't really interact with each other much. So in a way they're more like a gas than they are like a liquid. So aqueous solutions also have quite high entropy. Okay, so we're going to be interested in entropy change. And we're going to see that in some reactions you get a big increase in entropy, right? So if I burn something, let's say I burn a lump of carbon, so carbon's a solid, and oxygen's a gas. So I'm turning all of that solid into gas. So that will give us an increase in entropy right there. Carbon, very organised, solid particles together. But so would something like, if I took my sodium chloride solid and I added it to water and I made it into separate aqueous ions, hopefully this is reminding you of earlier lessons. So we've gone from 1 mole of solid particles to 2 moles of aqueous particles, which again are very high in entropy. So that would be a big positive increase in entropy. So anything where I increase the number of entities, okay, so I've got 2 moles of things here compared with 1 mole of a thing here, 1 to 2. And anywhere where I'm going from solids or liquids up to solutions and gases, those kinds of things are going to see an increase in entropy. And as far as the universe is concerned, an increase in entropy, an increase in disorder is downhill. Again, if I drop something onto the floor, it'll tend to spread out in a random way rather than staying together in an organized way. It's like things always tend to chaos. Yeah? Okay, so the symbol for entropy is S. So the symbol for entropy change will be delta S. So we're going to be looking at some changes in entropy here. Okay, and I'm just going to follow through the one I've got in the book here. So I've got a reaction where we're taking iron ore, that's a solid, and some carbon, that's a solid as well. And I'm making solid iron, but carbon dioxide gas. If I look at the entropy values for these, entropy, by the way, is measured in joules per Kelvin per mole, not kilojoules. We'll come back to that later on. It's quite important. So entropy 87.4 for the iron oxide, 5.7, very low entropy for carbon, must be very organised, 27.3 for solid iron, and 213.6 carbon dioxide. Of course, is a gas, so you would expect it to have the greatest entropy. Calculating delta S is a little bit like calculating delta H from enthalpy of formation data. So it's the sum of the entropies, the total entropies of the products, take away the sum of the entropy values for the reactants. Oh, I see. Yeah. Right, so let's do this. So we've got products. Again, we need to use the balancing numbers. Obviously, they still count. So 4 lots of 27.3 and 3 lots of 213.6 minus 2 lots of 87.4 and 3 lots of 5.7. Okay, so that's just a bit of number crunching, and it comes out to a big spiffing 558.1 joules per Kelvin per mole. Okay, that's a big increase in entropy. Again, it shouldn't be a surprise that it's an increase in entropy, because we've gone from 5 moles of solid to 7 moles of stuff, including 3 moles of gas. So we've got an increase in the number of entities from 5 to 7, and we've gone from solids up to solid and gas. So big increase in entropy there. So that would tell us that the reaction is probably very likely to happen. Yeah? Okay. If I said that negative delta H values are a sort of downhill for the universe and positive delta S values are downhill for the universe, then it sounds like if I could get some combination of delta H and delta S, kind of pool those two sets of ideas, I should be able to work out if an experiment is feasible. But I have to take into account something important. You might have noticed that delta S is measured in not just joules per mole, so delta H is kilojoules per mole, of course, it's joules per Kelvin per mole. In other words, temperature is important. If I look at a graph of entropy against temperature, if I started at 0 degrees Kelvin, then I would have zero entropy. By definition, there can't be any disorder if something is at 0 Kelvin, although of course we know that's thermodynamically impossible. As we increase the temperature, our entropy goes up. It'll suddenly jump when we get to the melting point. So we've got a solid here, and then just there was the melting point of our solid. And we're now dealing with a liquid. So the liquid will still increase in entropy as it gets hotter and hotter and hotter, and eventually that will turn into a gas. Then we'll get a very big increase in entropy, so that'll be our boiling point there, and now we're looking at a gas. So the key thing I'm trying to get across here is delta S is going to be temperature dependent. If I increase the temperature of anything, it's going to be a bigger increase in entropy. So when I'm putting the two together, I've got the delta H factor and I've got the delta S factor. I need to remember that the temperature affects delta S, so a bigger increase in temperature gives me a bigger delta S. So temperature is going to be a factor in deciding whether or not a reaction happens, which hopefully would make sense because think about it, something doesn't dissolve, you heat it up a bit, it will dissolve. So a lot of reactions are temperature dependent. We heat reactions up all the time, not just because that makes them faster, but because at lower temperatures they simply don't happen. Think of a really simple example, ice. Ice won't melt until we get to 0 degrees. It's not like it melts slowly at -10 and faster at 0. It won't, thermodynamically will not happen, it will not turn into water until we get to 0 degrees. All right, so let's do the same here. Let me just change colours. Get my data out. This is the delta HF data. Is that right? Yes, it is. -824.2. Carbon, of course, by definition, all elements in their standard states have 0 delta HF because delta HF is the enthalpy change when 1 mole of substance is formed from the elements in their standard states. All substances under standard conditions in their standard states. So if I've got carbon as a solid, 0 delta HF, same for iron, and then carbon dioxide -393.5. So I can work out the delta H, which remember is the sum of the delta HFs of products minus the sum of the delta HFs for the reactants, so similar to the calculation of delta S. And so I've got products, 3 lots of -393.5, take away 2 lots of minus 824.5. 2. And all of that is plus 467.9. Okay. Just one more thing before we go on. Negative delta H is kind of downhill, and positive delta S is downhill. So in other words, the signs are kind of the other way around. So if I take the delta H value and subtract the delta S value, taking T into account, I'll get an overall value which gives me an idea of whether or not the reaction will happen, will take place. And it's called delta G, that being the Gibbs Free Energy. And it's a made-up quantity given to us by combining the two thermodynamic assessments, the delta H and the delta S, the heat enthalpy change, the heat energy change, and the increase or change in disorder, taking temperature into account. Okay, so let's do that for this reaction. So let's say if temperature was 298 Kelvin, delta S we worked out was plus 558.1 joules per Kelvin per mole, when delta H was plus 467.9 kilojoules per mole. So let's stick all that in and see what happens. So delta H plus 467.9 minus temperature, which was 298. I hope I've got that right. Yep. Times delta S. Now, we just do that reminder again that delta S is in joules per Kelvin per mole, whereas of course delta H is kilojoules per mole. So I need to take account of that difference, and I do that simply by changing the joules per Kelvin per mole value into kilojoules by dividing by 1,000. So it's going to be 558.1. I'm just going to do that in red so you can see that clearly. Okay. What do we get there? Plus 301.6, and the units of delta G are kilojoules per mole. Okay, so what? Well, the law for Gibbs free energy, which has taken both enthalpy and entropy into account, is that if delta G is positive, the reaction will not happen. Will not happen at that temperature. Will not happen. We can use the term non-spontaneous, which is a bit of a mouthful, or we can just say it won't happen. So if I try and take iron ore, which is what iron oxide is, add it to some carbon and mix it around at 25 degrees centigrade, surprise, nothing happens. It's a big positive entropy, we're getting an increase in disorder, but thermodynamically there's not enough enthalpy change there's too positive an enthalpy change to make that entropy count. But remember, entropy is affected by temperature. So the reaction might not go at 298, or it doesn't go at 298 Kelvin, but it might go at a higher temperature. So what we want for a reaction that goes is delta G to be negative. So that means the reaction can happen. We use this word spontaneous, which doesn't quite mean for particles what it means for people. It doesn't mean that the iron oxide will suddenly decide to throw a party. It just means the reaction can happen. It's thermodynamically possible for it to happen. It doesn't give us any idea about rate. It could be a slow reaction, but it will go. So in between negative and positive is 0. Delta G equals 0 is kind of that inflection point when we can take a reaction that's not going to happen and turn it into a reaction that will happen. So let's do that. Just take away all of that stuff. So if we ask that question, and this is what AQA is going to ask, at what temperature does the reaction become feasible, is the word they're going to use. In other words, in theory, we can do it. Well, we'll just set delta G to 0. So now we've got 0 equals delta H minus T delta S. If I rearrange that, delta H equals T delta S, so therefore the temperature is delta H over delta S. Super. By the way, you are expected to learn the expression for delta G, like all mathematical equations in chemistry, apart from the Arrhenius equation, you are expected to learn them. All right, so let's find out at what temperature this reaction becomes feasible. So delta H 467.9, delta S, remember we still have to divide it by 1,000, not 0.558, I mean it will be 0.558, 558.1 over 1,000. And I don't remember what that is. 838.4. If you forget to divide by 1,000, by the way, so you do 467 over 558, well that will be less than 1. The reaction goes at 1 Kelvin, well that's slightly colder than deep space, so that should give you a clear indication that things have gone a little bit wrong. Remember, we're working in Kelvin, not degrees C. 838 Kelvin, that's more like it. That's, what's that? It's about 600 degrees. So if I can get my my iron oxide and carbon mixture up to 600 degrees, then things should start happening. We might want to increase the temperature more than that to make the reaction a bit more nippy. Okay, so we've done a few things here for entropy. Let's just do a quick roundup. So first of all, you should be able to spot when entropy increases in a reaction. So again, look for more entities and look for gases being formed. That's going to be an indication that entropy is going up. You should be able to calculate delta S as simply the sum of entropies of products minus reactants in just the same way you can calculate delta H. You should be able to use the equation delta G equals delta H minus T delta S. I should learn the equation delta G equals delta H minus T delta S to determine if a reaction is feasible. At a given temperature. And lastly, use T equals delta H over delta S to determine the temperature at which which a reaction becomes feasible. And remember, for both of those, we have to use delta S over 1,000 to change from joules per Kelvin per mole to kilojoules per Kelvin per mole. Last but not least, I think a quick sort of summary of things is interesting here. If I think about entropy, can either go up or down. And delta H can either go up or down. Let's start with delta H being endothermic and entropy increasing. So remember, entropy increasing, that's downhill. Delta H is endothermic, that's kind of uphill. So this is what we've just seen. We've just seen that in the equation here. Delta G is negative at higher temperatures. So if we heat it up enough, eventually we'll get to a point where the reaction will happen. A good example of that is dissolving any salt. If sodium chlorine doesn't dissolve, heat it up. Because entropy is positive, because we're making 2 moles of aqueous ions from a solid, and as I increase the temperature, that'll increase the entropy factor, and eventually it'll overcome the fact that the reaction's endothermic. Less disorder and delta H is positive. Well, there's nothing I can do. Reaction is not feasible or is not spontaneous at any temperature. I just can't do it. For example, I can't turn CO2 into diamonds. Sorry, it's not going to happen. It'd be nice if we could. We've got lots of CO2 and diamonds are shiny. All right, delta H negative exothermic reactions are downhill as far as the universe is concerned, and delta S positive is downhill as far as the universe is concerned. So if that's negative and that's positive, delta G is always negative. Reaction is feasible at any temperature. Yay! So combustion. So burning is always going to give me delta H negative. It's always going to give me an increase in entropy because I'm turning my solid or liquid fuel into lots and lots of hot vapor. So things should burn at low temperatures, of course. Whether that's actually feasible or not. I mean, not feasible. It is feasible. Whether it's practical or not is another question. But the thermodynamics is on our side. All right, so this last one's interesting. An exothermic reaction, but which decreases entropy. So delta G is only negative at lower temperatures. So over here, I had the fairly relatable scenario. The reaction doesn't go, I heat it up a bit, it goes. Down here, I've got a weird situation. The reaction doesn't go, I cool it down, and it goes. What kinds of things only happen at lower temperatures? Well, of course, freezing. Think about freezing. If I want to freeze some water, well, it's exothermic because I need to take heat energy away from the water into the surroundings. So it's an exothermic process, but it's definitely entropy negative. I'm going from liquid water, which is runny, molecules going all over the place, to something where the molecules are ordered in nice sort of crystal patterns. So I'm going to more order, so less entropy, less disorder. So I can only do that if I get it down below 0 degrees. So the lower the temperature, the easier it is to freeze water. So I think that just helps put a bit of context onto entropy and delta H and delta G, and stops it just becoming numbers. And you'll see these kind of questions in the multiple choice exam. You know, what do we have to have for delta H and delta S in order for the reaction to always be feasible, and so on. Okay, that's entropy.